Hi everyone, welcome to day 4. So today we are going to look at exponential smoothing models and ARIMA models. But before that, I'd like to very briefly recap what we have covered yesterday. So I'll share my screen. And please let me know if you can see my screen in case you can't. So I need to maybe change the screen.
Yeah, we can be able to see.
Wonderful. So let me just name it recap. Day 3. Okay, so let's start with bringing the FPP3 library here, loading the library. So we have looked at the different data sets so far. I'm going back to a data set called tourism. If you remember the monthly data set, the total overnight trips in Australia is a quarterly data set. We have region, state, purpose of travel and trips, and total of 304. Just to speed up a little bit the running time, I will group by the purpose of travel, and I will summarize the trips to be the sum of trips. So basically, I'm just looking at, okay, sorry, let's see what is going on. That sum shouldn't be like that. So we have the total trips for each purpose of travel. And if you remember, we had 4 purpose of travel, so we will get 4 time series. And I'll give this a name, maybe something like I'll just call it exactly that name. And just to be clear, this is the name, all right? So this is the data set that I'm going to use to specify models and train models on it. So where we have to start? Well, we take our testable data, we pass it to a function called model, and then inside model, we specify the name of models we want to use. So I start with the simple benchmarks. This is the name I give to the model. If you remember, or I can call it average, just to whatever name you want, this is your option. And then remember the functions, they're in capital letter in Fable. And for each forecasting method, you will get a function name. So here I need to provide the response, basically the column in my testable I want to use to produce forecast for. So here I have trips. Now I want to include more models. So I want to include naive as well. And if you remember, the function that we use for naive is in capital letter as well. And then I just use the same response variable. I want to include also seasonal naive. The function corresponding to seasonal naive is snaive. And then I put the response there as well. And then finally, we also had regression or time series linear model. I just name it as regression. The function that we use here is called TSLM, time series linear model. All right, and then I save this in a name called fit. And if I run this, and if I observe the fit, now I have my model table. And then here now I have 4 rows. And remember, in a Mabel, rows, they correspond to the number of time series. I have 4 time series, then I get 4 rows. And each column here corresponds to the model that I specified and trained there. All right. So for each model and each time series, I train my model and I get the trained information there. And if you want, you can go and look at the glance, for instance. If I want to stay with the pipe operator, so I put fit and then glance, and then you will get information about different models. You could use also tidy. So these are the sort of thing that you will practice later as well. And then if you try also the one we had called report. So the report one, it requires actually a single model. So we need to first select, let's say, the regression. Still doesn't work. You need also to filter the purpose to be, for instance, holiday. Let's see. And then now actually we can get the summary of the model. So the report is working with a single model. It cannot provide simultaneously everything about all models. All right. So following this, because we have now the trained model or the fit, we can produce the forecast. So we take the fit, we pass it to the function called forecast. And by the way, I haven't provided anything here, but if you want, you can always, for instance, for the regression one at least, you can provide the terms, like which one you want to use. So if I don't provide any term, the function will automatically, based on what is the default of the function, you'll get some inputs. All right, so here let's provide also an edge. Let's forecast only for 4 quarters ahead. And then let's call it a name, whatever. And this is what we call the forecast table or fable. And again, here, we need to know what each column corresponds to. So that model corresponds to the list of models we have here. So we will have actually 4 categories here. This is our index, basically is the quarters that we forecast ahead. And because we forecast only 4 quarters ahead, you will see it repeats. So Q1 2018, and then here you have Q1 2018 for a different model here. We also get the distribution based on normal distribution here for the trips, and then we get the dot mean, which is the point forecast. So if you want, you can also visualize this. So just simply passing this to auto plot, you will get a plot like this. So there are a lot of information there because we have 4 different models, the purpose of travel, and then 2 prediction intervals. So that's why it is not very probably helpful. If you want, you can put the level equal null, and then you see only point estimations. And if you want, you can also add the actuals before this as well. Is there any questions so far based on what we have covered? Right. So another thing that we did yesterday, which I think it is interesting to know, is how to visualize these distributions, right? Well, maybe before that, I will just do one more thing here. So you can visualize your forecast. You can also plot it with your data. And then another thing that you could do is, basically this is, you take your fable or whatever name you have here, and then you pass it to high-low. And then here you can provide a level, let's say 90%. So if I run this, now I get my prediction interval for 90% coverage here. This is the lower bound, and this is the upper bound of the prediction interval. If you want to get them, the lower bound and upper bound, in two separate columns, you can use this function unpack hilo, and then just type this name inside quotes there. And then here we go. So we have now 90% lower bound, 90% upper bound, the point forecast, right, which is between these two, and then the entire distribution. So if you want to extract prediction intervals, you can do that as well. And then finally, I wanted to show you how we could visualize. So I take how we could visualize the distribution. This is something we did yesterday. I don't know whether you did follow or not, but we can do it as well. So I do it with ggplot. And then here I put the quarter in the x-axis, or we could put it in y-axis, but let's start with putting it in x-axis. I think that makes more sense because it's time. We always want to put time in x-axis to see the evolution. And then here actually we use a new package. So if you haven't used it, you can install it and then we use it, ggdist. So I need to load this package as well. And then here I will provide a new argument called ydist. So this is for distributions. And then which column I want? I want this column, which has my distributions. So I could just copy and paste it there as well. All right, so this is, again, ggplot2. If you have used tidyverse before, you should be able to create this kind of thing. And then I need a new function here. I just type stat, underscore half. So half I, this is from ggdist, as we can see. And then I could create a facet as well, because here I have different purpose of travel. So for each purpose of travel, I will get one separate plot in a sort of like a panel. And then I could add any sort of labels, if you like, to this. So X, Y, a title. So my X is quarter. My Y is trips. I could add the title like forecast distributions of trips. Okay, so let's see if I run this, what happens? Okay, actually nothing happens. I think something. So I have, oh, sorry. This is, again, I make mistakes. So this is sometimes happens. So I forgot actually to put the iStatic there, which is a function that you need in ggplot2. Okay, so if you do that, now you can actually get this. I will just add one more thing. I like this theme quite a lot. Let's see if it works. Okay, so if you do that, now you get basically a sort of a distribution of what we have forecasted, and it is interesting to see, for instance, for the other, which is the one here, the distribution is narrow, but then we have different sort of distributions for the other purpose of travel. So this is something you could also explore it later, but I think it is interesting to see how we can visualize the forecast of the distribution as well. Okay, so there is a question here. No, it doesn't actually mean the same thing. So when we specify the horizon, as we discussed yesterday, we can specify the horizon in two different ways. So if you use quotes, and inside quote you use like a plain English thing. For instance, if I say 4 years, so this 4 years somehow basically is related to our tissable. Okay, so here, what is the temporal granularity of my tissable is a quarterly, so it's quarterly time series. So if I say 4 years, basically 4 years of the forecast, because I have quarterly time series, it means 4 times 4. So in that case, if I want to have exactly the same thing, this would be the equivalent of that. All right. Okay, so you can always provide that, but if you provide a number, it means you know that what is the temporal granularity here. So if you change this to 2 years, then the equivalent of this would be 8. Okay, so if you have monthly data here, then you see 1M. So if you want to forecast for 12 months ahead, then you have 12 here. If you want to forecast for 2 years ahead, 24 months, you put it like that, and that would be, again, the equivalent of that, because if I have monthly data, this would be 1M. All right, so this is what we have done yesterday. And what is really important, and it is fantastic, what the way Fable or Tidyverse is designed, which is the collection of these packages we use. Now, whatever we have done here, you can repeat it with any model that we use later. So the only thing that changes really is here I add more models. The rest, I'm using the same sort of function to understand what is inside each fitted model, the way I produce the forecast, the way I plot, and so on. Okay, so this was a couple of important things that we have covered yesterday. Is there any question before I move to a new topic? It's a good question. I have never tried. Let me try. And one thing that you can always do is you can always try things, okay, in R and see whether it works. It doesn't work. So there should be a relationship between the sort of thing that you put here. But I think 1 year, for instance, if I put it 1 year, sorry. So that works, and then if you change it to, so 2, 3, it will work. And again, it actually works with years and year both as well. I think it is going to be the same. Yeah, Mitch is there, says Quanta doesn't work, but days, week, months, year works, okay? Wonderful. Okay, so now let's go to the next topic, which is exponential smoothing models. So in this session, I will introduce the exponential smoothing models, and we will discuss what sort of components these models will take into account. These are two important components we have discussed in day, I think, 2, trend and seasonality, but also level that we have discussed there. So we will see how this exponential smoothing models will take into account these components. And then we show you the taxonomy of exponential smoothing, a sort of categorization of them and how we can use them with R. And then at the end, we also look at what we have already seen actually about using Bootstrap to produce many possible futures, which is non-Gaussian forecast distributions. All right, so you remember 2 simple benchmarks we have covered yesterday, naive and average. So if you think about naive method is relying only on one observation, which is the last observation. But the average or total average or mean is relying on all observations that we have seen before. Basically, if you think about the forecast, so for maybe I'll use a different color, just color. Okay, so this is my forecast, T plus H hat. So if you use naive, you say my forecast for the future equals to last observation, whatever I observed the period before. But the average one, you say T plus H equals to something like this. Because you add everything together from the beginning, okay? So observation in period 1, in period 2, and then you go like that until the last observation. And then you divide this by total number of observations. So we will use T for that, but you can use N or any other number. So this means we have something like this, 1 divided by T multiplied by Y1 plus 1 divided by T multiplied by Y2, and so on. Okay, so as you can see, when we use total average, we give a weighting to all observations, and all observations, they have the same weight. So when it comes to naive, we say the only observation that matters, or the only period that matters, is the previous period. What happened, it is very important, so I give the 100% weight to that. In average, you say all observations are important equally, and I give them the same weight or importance, right? But sometimes you may want something between these two, which actually makes sense. You say, well, I can define a mechanism, a sort of a weighting mechanism that gives higher weight to more recent observation, and this weight can actually decrease as we go to the past. So older observations will have less weight. Recent observation, they have higher weights. And this is exactly the concept behind exponential smoothing models. Okay, so in the exponential smoothing, I'll just do this. I think I can clear that. Okay, so in exponential smoothing, basically I can write that forecast that I mentioned as something like this equation. So I introduce that weighting using a parameter called alpha. We call this a smoothing constant. So I say I can define that forecast as alpha yt, then another weight, which is the multiplication of alpha by 1 minus alpha, and multiply this by the observation before, the third observation, and I go back, you'll have a weight of alpha 1 minus alpha square, and so on. Okay, so I can actually write this forecast of exponential smoothing that we discuss in terms of how weights are distributed like this, and this is the simplest exponential smoothing. So we call it single or simple exponential smoothing. So if you see SES, so SES refers to this simple exponential smoothing. So why we call it exponential? Because if, let's say, we have a weighting system like this, so we will have the highest weight for the most recent observation, which is in period t, and then we have period t minus 1, period t minus 2, and so on. It goes back like that to the first period. So we have always the highest weight for period t, which what you see here as alpha. So this is alpha, and then the weight for this one is alpha times alpha minus 1. The other one is here, the other one is here. So as you can see, if you link them together, so from period t to period 1, the weight is decreasing exponentially. So the name basically comes from this concept. All right, so we had two benchmarks, naive and total average. Naive gives 100% weight to most recent observation. Average gives equal weight to all observations. We need something between. And exponential smoothing, simple exponential smoothing gives us this. We introduce a weighting mechanism by introducing a parameter called alpha. And alpha can change between 0 and 1. Right? And then we created this weights from the most recent to the first observation. Now you can tell me what happens if alpha equals 1. Can you put it in the chat? What happens if I put alpha equal to 1? Okay. Yeah, so absolutely. So if you basically put alpha equal to 1 here, this becomes naive, and then you can also put alpha equal to 0, and then you will get something else, which is something called initial value. I'll show you a bit later. Okay. Wonderful. Now, this is a classification called Peggle's classification. It shows you visually what exponential smoothing is capable in terms of capturing different patterns. So you may deal with a time series where there is no trend and no seasonality, right? So you'll get like just a level, basically, a smooth line in a very artificial world. You will get just a horizontal line. But as we showed you, when it comes to level, we have always randomness, so you'll get a level but with some fluctuations around it because of the randomness. So you may have seasonality, which could be additive or multiplicative. You will have trend, which could be additive damped. So basically damping, as you can see here, additive could decrease or increase, but damped, it goes and saturates at some point. We could also have for the trend, we could have increasing or decreasing. So it is something similar to this, but in the other way around. And we can have a combination of the trend and seasonality as well. We could have also multiplicative trend, but so these are not very good in forecasting. So they are not actually covered or not recommended, at least, to be used in practice. So this shows us visually what sort of patterns exponential smoothing can capture. So these methods are quite old. So here I'm talking about methods, because sometimes we distinguish between a method and a model. So basically, in exponential smoothing, when we say methods, and again, you may recall from textbooks, some textbooks use single exponential smoothing, Holt, Winter. So these are actually methods, and they produce only the point forecast. And these methods, they go back to 1950s and 1960s. But more recently, so actually people in Monash University, they have developed a way that exponential smoothing methods can also include an error term, and that became exponential smoothing state space model. Now, those are models because they're capable of producing probabilistic forecasts, and they allow also for a better way of estimating the parameters. So these are like all models. They have been there for actually many years. And even recently, not recently, I mean, in some forecasting competitions. So there are many forecasting competition, M1, M2, M4, and the last one was M6. Exponential smoothing models, they perform consistently well, I would say. So what they do, well, exponential smoothing models, they try to combine level, trend, and seasonal component. And then by combining them, they can describe what happens in a time series. So this is one thing. The second thing is these components may change over time, and exponential smoothing includes also parameters called smoothing parameter to control how these components can change over time. So we have alpha, beta, gamma. So alpha is for the level, beta is for trend, and gamma is for seasonality, and we'll see them in the equations later. And of course, we need to choose the values for alpha, beta, gamma, but also we need to understand which components we need to include in the model. Okay, so in a exponential smoothing model, we want a model that captures the level, impurity, trend impurity, and seasonality impurity. And the question is, how do we combine these components? We can combine them additively, as you can see. Okay, level plus trend plus seasonality and plus an error term. We can also combine them multiplicatively, so by multiplying these different components by also the error part. Or we could have a mix. Some part, we can combine them additively and then multiplicatively with others. So another important thing when it comes to exponential smoothing then is how these components can change over time, and these are the role of exponential smoothing parameters, alpha, beta, and gamma. So now one important notation that you will see a lot later in R is this ETS, which could refer to exponential smoothing as you can see here, but more importantly is it tells you in ETS we have three components that we need to remember as we go actually to use R later. These are really important as well. So the E refers to error, the T refers to trend, and S refers to season. So the error can be additive or multiplicative. So these letters, you need to remember them. So A means additive, M means multiplicative. Trend, it can be none, so there is no trend. It could be additive, the letter A is used for that, or it could be multiplicative. And this is something I said, it is not recommended, but you can have them here as well. And it could be also damped. So if you have additive trend that is damped, you use AD for that. For the seasonality part, you could have none, so we use letter N for it, letter A for additive seasonality, and letter M for multiplicative seasonality. Now let me introduce the equations that we use, because what happens in exponential smoothing is we have, for each components that we discussed, level, trend, and seasonality, we have a corresponding equation. And then we have also a mechanism to combine these different components to create a forecast. And these are different forms of representing exponential smoothing methods and models. The form that we see here has a forecast equation, a measurement equation, and a state equation. So the state equation tells us how the component evolves over time. So in this case, because we are dealing with ETS, A, and N, it means we have no trend and no seasonality. Basically, this corresponds to a simple or single exponential smoothing model that we discussed earlier. And then we have the measurement that shows the relationship between the observation and the state equation. And then we have now an epsilon t, which follows a normal distribution with a mean 0 and a variance of sigma square. So these are innovations or single source of error, because as you can see, both the measurement equation or state equation, they use the same epsilon here. Okay, and then that's what I explained in terms of how measurement captures that relationship between what we observe and the component that changed, which we call it a state. And then the state is how that component changes over time. And alpha is a smoothing constant. If you want to have the multiplicative version of it for the error part, because the others, trend and seasonality, they are still none, we can write it in this way. So as you can see, instead of having the additive one, which is take the level, the estimated level in the previous period plus alpha times epsilon t, which is the error here, we multiply that. So one important observation, the models with additive and multiplicative errors with the same parameters, they generate the same point forecast. However, the prediction intervals is different. All right, we can now maybe go to R just to have an example looking at this. Maybe I will have a look at the Q&A to see what is here. Yeah, so that's correct. In that example of simple or single exponential smoothing, the sum should add to 1. Okay. All right, so let me open my RStudio. I think this is the, okay. So let's call this ETS. So we can, well, take any example that we had before. For instance, we can take the example of a global economy. So this is what we have used before as well. All right. So this is our testable. It's a yearly testable. We have 263 countries, 263 time series. Okay, so similar to what we did before, I take my testable, pass it to model, and then I have to choose a name. I can choose something like this, or whatever you think is relevant. Or simply I could say single exponential smoothing, something like that. All right. So now a new function, the function that we need to use for exponential smoothing models is called ETS, right? And the first argument we need to provide is what you want to forecast. For instance, we could, I don't know, forecast export, if you like. I can leave it as it is. This is something we call it an automatic ETS. I'll come back to it at the end to see how automatic ETS works. But at the moment, let's see how we can determine these 3 components. So remember ETS, we have 3 components: error, trend, and season. So there are 3 specific functions for that in ETS. So if I want to error, if I want to specify them, basically you can also here go and look at the help file of this, so it will give you some information about that here as well, right? It should be somewhere a specific function. So yeah, you have the error, trend, and then season, and each of these specific functions, they have a lot of different arguments there as well. But we want just to focus on the first one, which is I have this specific functions and I want to specify single exponential smoothing if this is something of interest. So let's say I put the error term to be additive, and then I have my second term, which is trend. Then I put n here to be none, and then I have my third specific function, which is season, and I put n here as well. So if I just run this, well, there are a lot of countries. I could maybe focus on just one country, I would say. I just maybe stop. I filter. Maybe I put the country, or I put the country code. It could be. Let's see what happens if we do that. All right, so now we focus on Australia only. So because it's one time series, then we get one row, and then we have one method, we get one column. Okay, so this is my bit. And then you can actually look at the report. I mean, all the functions that we had before. And again, I repeat, this is the beauty of this, because everything that you used before, you can use it with new methods. Okay, so glance gives you the information about sigma square. Okay, I think this should be actually this one. Yeah. So the information about sigma square, the log likelihood, the information criteria, etc. Tidy, here it gives information about alpha and L0. So L0 is another parameter. So when we have exponential smoothing, basically they have to start the process at some point. And the process basically goes to the beginning of the time series. And when we start the process of, because exponential smoothing, they are recursive calculations. So we start from the beginning and then we go do the calculations to the last observation that we have to get the fitted values. So to start this process, we need something in simple exponential smoothing called L0. This is for level 0. And if you follow the equations, actually, you can derive that as well yourself. You can replace t with 1, 2, 3, up to any observation that you have. And if you write down the L equation, you will see that to calculate L1, you need to have an estimation for L0, which is the initial value. And that's what it refers to. So Tidy will give you that. And if you look at the report tells us what is the model that we fit here. It also gives us the parameters and then the other information that we have seen before. To forecast, I take my fit and then I pass it to forecast function and I put an H there as well. So it provides me with the probabilistic forecast or distributions and point forecast, and I could also go and plot them. I think you could also add the line if you like there. So if you want to specify and tell your function, I want single exponential smoothing, this is what we do. And actually, this is what we specify all the models that we cover later as well. All right, let me go back to my slides. And if you want to specify the multiplicative one, just replace the A with M, okay? Now, what if we have the trend components? Because simple exponential smoothing, or what we have seen here as M and N or A and N, they capture only the level. And actually, depending on the value of the alpha that we have, it could be more reactive, because remember, if alpha is close to 1, it becomes similar to naive. So it reacts quite a lot. If alpha is very small, the sort of like fitted line that we get is very, very smooth. So these two models, they can capture level, but no trend and seasonality. So if you want to get the trend and add it to this, we need a new state equation. We need an equation to tell us how level changes over time and how we add level to other state equations, and then how this will be added to the measurement equation as well, and at the end to the forecast equation. So here, as you can see, we get a new equation that corresponds to the trend. So trend at time B equals to what we have in the previous period plus beta times the epsilon t. Again, epsilon t is the same, follows the normal distribution as before. And this beta tells us how we control the change of the trend. If beta is 0, the rate of change, the trend doesn't change, right? So if we put beta equal to 0 here, this will disappear from here. So it means the trend in period t will be the same as the previous one. So now we have two equations. So in simple exponential smoothing, we have one state equation, but now I have a level, and then I have also a trend, and I add them additively, and I get my forecast equation. And as you can see here now, I have my H, which is forecast horizon, multiplied by B, which is the trend. So it means now I can capture the trend if it exists in my time series. The multiplicative version of it is, again, is quite similar in terms of how we do things. But instead of having that error term being simply the difference between the actual and estimated, is a relative, basically, error, which is actual minus forecast divided by the forecast. That's how we define that error term there. No, this is not actually mandatory to determine error, trend, and seasonality. As I said, I will come to this at the end, but I just wanted to show you, if you want to tell your ETS function or exponential smoothing model what is the model that you want to fit into your data, you can use that tree-specific function, error, trend, and season. If you ignore them and then use just an ETS with your variable that you want to forecast, ETS will do the job, and we'll talk about this in a bit. Okay, well, maybe I can show you this example here as well. I think this is sort of like an automatic one. I can go to our studio. Okay, I think this time we look at the population. Let me see. Yeah, we look at the same sort of country here. So I have my global economy. I filter country to be Australia, but you can do it with any other country if you like. And then this time, I want to actually get the population, to forecast the population of Australia. And I want to divide the population that we see here . So this column, I will divide it by 1e6 to be represented as million. And then I give it a new name. So this will give me a new column here. It's population in million. And then I just call it Aus economy is a new name. So I pass this tessable to model function, and then inside model function I have my ETS, and I tell my ETS function what I want to forecast or look at. What is the measurement variable? I call it fit. But if you look at the fit, this is again what you see. you can look at the report of this fit. So it tells me that the model that is selected for this is ETS-ANN. As I said, I will come back to this, how the model is selected if you don't provide anything here. So here I didn't provide error or trend or season. So the algorithm goes automatically picks this model as the best model for this time series. So it tells me the error term is additive, the trend is additive, and there is no seasonality in the data. And if I go and maybe auto plot this, you can see that clearly it has a trend, and then there is no seasonality. Actually, sometimes you can, especially for maybe monthly and quarterly data, I have used it in the past. Sometimes if you want to see whether the time series that you look at has trend and seasonality, you can run an ETS like this and look at the report of it and see what it returns. This could be sometimes a good indication whether your model contains trend or seasonality. As I said, for quarterly and monthly, it is quite good. So another actually function that is quite helpful with these models and with ARIMA and regression as well, and we have used it yesterday, is called components. So if you take your Mabel and pass it to components and you run, you see the equations that I mentioned in the slide. So here is the level. This corresponds to the state equation, which has LT in it. If you see the slope here, this corresponds to the equation that we have BT in it. Right, and the remainder is the epsilon T that we see there. And you can also go and plot them. And this is somehow, if you remember, we did STL decomposition, somehow similar to that, because we have the population, and then here we have the level, we have the trend, so how the trend changes a little bit, and then we have the remainder part of it. Okay, so we look at the plot of the population in Australia. It looks like this. So there is no seasonality in it, and we expect ETS to perform well here because it returns an ETS with a trend which is quite strong and present here, and no seasonality, and this is what ETS did here. All right. I think we look at here, yeah, we need to do maybe the forecasting for it as well. So if we do the forecasting, we take the fit, we pass it to the forecast function, and then let's forecast for 10 years. Okay, and then if I want to plot it, I simply plot the forecast there. If I want to include the data as well, you can do it like that. And it seems like this is really a good forecast for this because the prediction intervals are quite narrow as well. All right, so this is how you use exponential smoothing if you don't provide any components inside it, like the specific function, error, trend, or season. All right, so if you have a damped trend, we will add a new parameter called phi. Right, so and this parameter, as you can see, is multiplied by the trend, because remember, we said if you have only trend, which is increasing or decreasing, maybe it doesn't make sense to be like that forever. We want this to saturate at some point, and that's the sort of shape I showed you in the Pegel classification. We can actually get that by adding a new parameter called phi. So one thing that you may observe is, as we started with exponential smoothing, the model was quite simple. We have one state equation L and one smoothing constant alpha, and then we have one initial value called L0 as well that we need to start the process. As we add more equations, we will get more parameters. So we have a beta. Now we add one more parameter for the damp trend called phi. So the models, they become a bit more complicated comparing to the first one, because we will add more parameters to this. So we can add a damped trend as well, the same way. And then this will help us to get the damped or long run forecast that becomes saturated or constant. So if you want to do that, it is quite easy. So you go inside the trend function and you say that I want my trend to be additive and damped. And you don't change anything in the error or season part. Okay, I think this is something we have looked at as well. So what about seasonality? Well, if you want to add seasonality in exponential smoothing, we need to add one state equation for that as well to see how seasonality changes over time. So this will basically talk about the evolution of the seasonality, and that's why we have a parameter called gamma here. Again, if this is 0, it means the seasonality in period T equals to the previous sort of seasonality we had. M here refers to the number of seasons we have. This depends on the temporal granularity. If you have monthly time series, M is 12. If you have quarterly time series, M is 4, for instance. So we can also add seasonality to the equations, and this is the additive form of it, but we can also have the multiplicative form. And of course, all the parameters that we discuss here, they have also a range that need to be respected. And these are included automatically in the ETS function. So this is the multiplicative version of the seasonality that we include. So one thing that you need to remember is actually this STs, right? So we call them also seasonal indices. So for each season that you have in your time series, we get one indices. And again, here season refers to that period really. So if you have quarterly data, you will get 4 S for it. Each S corresponds to 1 quarter. So for the, let's say, first year, you get 4. For the second year, you get 4, and so on. And this could be also added additively or multiplicatively. Well, let's look at this example of the tourism, because it has some seasonality in it, and then let's see how ETS models that one. So I will take the data set that we have used before, which is tourism. Okay, is it sorry, all right. So this is the data set. I will go and focus on the purpose of holidays, just to be holidays, purpose of travel to be holidays. So if you do that, then you get now this testable, which has only holidays. We have 70 6 time series this time. Let's give it a new name called holiday. Okay, and then I go and take the holiday, I pass it to model. Let's just give it a name called ETS. And then you shouldn't confuse this with this, right? Because this is a name that you provide. If you don't provide any name, what happens is R goes and put this as a name. We prefer to provide a name because it's easier to work with in case you need to do it later. And so just let's call it ETS. And then I put it inside a new name called fit. As you can see now, it takes a few more seconds probably to fit the models because it used an automatic algorithm here, and also we have more time series. So now you can see that we have many rows, 76. Each row, remember, corresponds to 1 time series. So if you want to maybe go and focus on any part of this, for instance, if you want to focus on any specific region, right? And let's say I focus on a region called the Snowy Mountain. Should be affected by seasonal components. Then if I look at the report, okay, so basically what it returns no trend and then an additive seasonality here. And if you go and look at the component of this, so I just copy this, paste it here, and then change this to components. Okay, so this time I see that I have a level. There is no slope here because the model didn't return any. It says there is no trend, right? So we didn't get any column for that because we wouldn't have that equation there. And then we have now season. And then we have the remainder part as well. So these are the S components that I was mentioning. So for each quarter and then also the corresponding region, state, and purpose, we will get those. So for each one, we will get 1, and then for each year, we have 4 of those seasonal indices. Okay, so if you want, you can also plot them, the components for this one. And then here you can actually see the seasonality better. So you can see that consistent repetitive pattern that we see in the seasonal. We haven't plotted them, but well, you see actually the plot here at the top as well, the trips. All right, so you can look at the components separately if you like. Okay, I think I have 15 minutes, so I need to speed up a little bit here. So I have looked at this example. Okay, so this is basically the taxonomy of the ETS. So we have looked at them before. So we have a column for trend, another one for seasonal components, and then we have 2 types of errors, additive or multiplicative. And the combination of this will create different models. In total, as you can see, we have 9 here, right? And then 9 here, so we'll have 18 different models. So this model sometimes could be numerically unstable. And this is because if you look at the equation, sometimes you in the state equation, you divide by something, and sometimes that something could be probably close to 0. So that may cause issues. So that's why they're not stable. Sometimes also this type of multiplicative seasonality models wouldn't be useful if you are dealing with a time series that contains low volume or zeros. So you need just to be aware of that as well. So now how ETS estimates parameters. So because remember, if you look at all the equations, first of all, ETS model needs to decide which component should be included. So is it L, is it B, is it S, or all of them? And then how to combine them, additively, multiplicatively, or mixed. So that's one thing. And the second thing is we have to also estimate the parameters. So we have smoothing parameters, alpha, beta, gamma, and phi. So alpha for level, beta for trend, gamma for seasonality, and phi for the damped trend. And then we have also initial values for each component. So we have L0 for the level, because that's where we have to start. We need that value to start the calculation. We need a B0 to start the calculation for the equation of the level. And then we need also a collection of the seasonal indices, right? So this depends on the temporal granularity. So we need also to get the initial values for these components. If you have quarterly time series, you need 4 of them. If you have monthly time series, you need 12 of them. So these are automatically calculated by the function using maximum likelihood estimation. And if you have like additive models only in ETS, this is exactly the same as minimizing sum of square error that we have seen in the regression. But for the multiplicative error, they are not the same. So the question is how models are selected in the ETS. Well, they are selected using information criteria. Again, we have seen information criteria before. In general, information criteria could be seen as a combination of 2 things. One is how good is the fit? Because when you create fitted values, so if yesterday we actually draw the actuals and the fitted values, so how close actually that fit is to the actual, but you know that we can always get a good fit by adding more parameters. This is something we call it overfitting. So we don't want the model to be overfit. So that's why we add a second part to the information criteria, which gives a penalty to the number of parameters that we include in the model. So information criteria tries to balance this, so avoid overfitting, get a fit with a reasonable, good fit with a reasonable number of parameters. So ETS is using the corrected AIC, but the others are also provided. AIC and BIC criteria are also reported if you use ETS, similar to other methods that we use. So this is a nice property. Basically, if minimizing the information criteria, assuming that the residuals are following a normal distribution, is equivalent of minimizing 1-step time series cross-validation for the mean square error. This is a really nice property of this information criteria if this is something we focus on for the 1 step ahead. Okay, so now how ETS function works. Well, this is something that, again, Mitch, PhD student, Rob Heinemann, Mitch, supervisor, not PhD student, Rob Heinemann and colleagues, they created this automatic function called ETS. So it applies each model that we saw among those 18 different models to the data and optimize parameters and initial values using maximum likelihood estimation. It selects best method using AICC, so by comparing different components of it, then produce a forecast for the best method. And then we can get forecast for the prediction intervals. And as I said, this method actually performs quite well in forecast computations. So now what if we want to produce a forecast that is not is not following that assumption of residuals as normal distribution? We have actually looked at this before, but we can look at this by this example from Aus Retail and focusing on the state of Victoria, and then also cafes, restaurants, and catering services. So I have recently, well, in November and October, visited Australia last year, and I can confirm that the coffee is good there. So we can look at the time plot of this. So in the y-axis, we see the turnover. In the x-axis, we see the time. And it is months there. So we may need to do a transformation here because, again, you remember that the sort of seasonality you see at the beginning is smaller than what you see here. So we do a box-cox transformation first. Now it seems a bit better. We can use ETS now. I think we have discussed it before as well. What happens if you want to use transformation with Fable? Fable takes care of transformation automatically. So here I want to forecast turnover, but I wanted to transform it first and then produce the forecast. So basically what you need to do is just put the function that you have for the transformation right before the forecast you want to, the variable you want to forecast, and then put the name of the forecasting model function there, and it will does the job. So the rest of this is really similar to what we did before. We have our Mabel, we pass it to the forecast, and then we produce the forecast. But as you can see now, it is not in a normal distribution. This is because we did a transformation. But the point forecast, it is transformed back to the original scale, so we don't need to be worried about that. So that is completely fine. So if you want to do transformation, just put the function that you want to use for the transformation before the response variable, and the functions will take care of the rest. Okay, so I think this is the one we wanted to focus on, and I showed it to you yesterday as well. So for the same fit, we can use the generate function, create different possible futures, and then for 3 years, we need to make sure the bootstrap is equal to true in this case. And remember here, we are using ETS because our fit is actually here, right? So we use the ETS function. You will get this different possible futures. And then if you visualize them, this is different sort of possible futures that we have here. And you can also use the forecast function directly for the bootstrapping. Rather than going through generate, we can just pass the fit to the forecast. And this will give you also the forecast generated by the bootstrapping. And you can plot them as well. I think I have maybe 5 minutes. I'll see if there is any question. And maybe I can quickly also show you this example of the cafe here. Okay, let me see. Yeah, so why gamma is introduced? So is a good question. So remember, in any equation that we introduce here, so we started with something very simple with the first one. So we have only one equation which has the level. Then we introduce the trend. So we bring another equation. And then here we bring seasonality. So we introduce the gamma because we want to control how seasonality changes. If this is 0, it means you don't have this part. So there is no gamma. It means seasonality is going to be fixed always. So whatever you want to get in ST, which is the seasonal index for the period T, is equal to the previous one. So ST minus M. So M refers to the number of seasons. If you have quarterly, so M is 4. So the seasonal index, let's say for the Q1 of this year, equals to the seasonal index of the Q1 of the year before, if it is quarterly, and if gamma is 0. So we introduce a smoothing constant like gamma, beta, and alpha to control the change of these components over time. And we leave it also to the ETS function to do it automatically. I think there was maybe something here.
There is another question in the chat.
Yeah, so, well, in terms of how did we know either additive or multiplicative method we have to use, so when we visualize the time series, if you remember, we explained how we know that a part of the time plot shows you whether you have additive or multiplicative seasonality. If the length or the magnitude of the seasonality changes with the trend, as trend changes, it becomes bigger, right? Something like this. So if I do something like that, not 100% maybe, but something like that. Do you see? So as this is, for instance, the level of the trend. So if this changes, you see here, this distance is quite smaller comparing to, so here, this is what we get. Here, this is what we get. So this box is much bigger than this one. So if you have something like that, then you deal with a multiplicative one. But if you have something where is, so this is a nice one. So it doesn't matter where you look at it. So if I put my level here as well, so it doesn't matter where you look at it, this actually length and this is, they are the same, right? So this is a additive seasonality. So you can always do something like that, but you don't really need to bother with, if you use ETS, it will automatically gives you that. But if you want to also provide it manually, you can do it. And this is an indication of whether the time series has additive or multiplicative seasonality. Well, I mean the generate, I because it is doing exactly the same thing as forecast. So if you produce the forecast, sorry, let me close this first because okay. Yeah, so in I use generate sometimes because I can create those. If I show you the example here, so I can show people how actually these different possible futures are created, because this is related to this .sim here. This is something that I use generate for to get this and create those possible futures that we were talking about in probabilistic forecasting. If you use forecast directly, it wouldn't actually show them like that. It'll pack them inside this sample, right? And so that's one purpose I used the generate for, just to visualize it like that. I don't know if there is any other purpose, whether Mitch is there that could be used, that Mitch is aware of. Okay, I think we can have a break, about 15 minutes. So when we are back, we'll see whether there is any question that we can address. If not, probably we'll start with doing one example in ETS and then talking about the second family of models in ARIMA. All right. Well, I hope you had a good break. Okay, so let me recap on what we have covered this morning. So this morning we talk about exponential smoothing models. So the idea of exponential smoothing models comes from 1950s, 1960s, where we introduced simple or single exponential smoothing. Why? Because we had simple benchmarks like naive, where it takes 100% weight or gives 100% weight to the most recent observation. And also we had average method, which gives the weight to all observations in the time series and actually gives them an equal weight. But we wanted something between, and this is where simple exponential smoothing comes in, because it says I can define a mechanism, and that mechanism helps to introduce a weighting system, and this weighting system gives a higher weight to most recent observation, and then lower weight to older observation. And this is the idea of simple exponential smoothing. So in these models, we start with that, which is the simplest case, where we have only the level, right? So we have level. In addition to level, we have also trend and seasonality. So if there is no trend, no seasonality in your data, probably the best model you can use in the family of exponential smoothing is the ANN, which corresponds to that simple or single exponential smoothing. Now, if your time series has trend or seasonality or combination of both, exponential smoothing can deal with that. So we have these components. We can combine them in different ways, additively, multiplicatively, or mixed. And we can also determine parameters like alpha, beta, gamma to say how these different components can evolve over time. One option is they don't evolve at all, and actually those parameters can also provide those values, but we leave it to the exponential smoothing or ETS function algorithm to pick those values automatically. There is no need really to do it manually. Maybe there are some exceptions where you may want to do it. Maybe also you can do it for just educational purposes. So if you want to learn how alpha, beta, gamma affects the fitting, you can always go and change those values. Otherwise, in real world practices, you don't really need to do it. You can leave it to ETS to do the job. Okay, so to summarize, in ETS, we have different components. We combine them in different ways, and then we have this different parameters that we need to estimate that allow us to control how the rate of these different levels can change over time. Okay, so now let me briefly talk about that that example that I mentioned, and then we can talk about ARIMA after that. So one package that is part of FPP3 is called, I don't know whether you use it during this a couple of days, but it's called testable data. And this actually contains many data sets, including those we have used so far during the lecture. So you can always go and play with them. If you want to know what each data set is, just take the name basically there, go to the console, put a question mark, type the name, and then you get the information about that data set. So you can use them for learning, if you like, as well. So here, I'm interested in a data set that is about house retail. So if, again, you look at the health file here, this is a monthly testable data set. Is as a turnover of retail industry in Australia in million Australian dollar. Okay, so this is the data set. It's a monthly data set, 152 different time series for different state and industry. Well, we want to just focus on one state. So if you know, I think we used this before. So if you want to know how many different values you have, there are different ways of doing it. One way is using this thing to see how many values we get in a state. So we have different 8 different states, and then if I want to know how many I have in industry, I think that I have more here, so 20 different industries. All right, so I want to focus on state of Victoria, which is this one. So I filter state Victoria, and then I want also to focus on one specific industry, which is cafe, restaurant, and catering services. So this one, the first one. Okay, so if I do that, you'll see now I have one time series only. So another important thing that I want to mention is when you write your code, you can, of course, focus on many time series. I could do the forecasting for this data, which contains 152, or only for this one. The modeling and forecasting and evaluation and everything that we see here is almost the same, really. And this is very important to remember, right? So what we need is a testable. That testable could be one time series, could be many time series. But the process that we go through to fit models using model function and to produce forecasts using forecast function, to extract prediction intervals, generate distribution, is going to be almost identical. Okay, so now this is actually what we have, and because I have only one time series, I don't need to have all these columns. So I'm going to go and select the columns that I need, which is the months and turnover. Okay, because there's only one time series and it is for this state and this industry. Okay, and this will give me now a simpler version of it, which has the index and the measurement, or the variable I want to use for the forecasting. And let's call this Cafe Victoria. Okay. If you want, we can plot this. Okay, so you see that there is a sort of a trend, some repetitive or consistent pattern as well. And then you can guess that actually this is a sort of multiplicative seasonality. Okay, it is clear that the magnitude here is lower than what we see here. Actually, the idea of additive error and multiplicative error is more or less the same as well. So when we say additive error, it means the errors here and there, they are similar in terms of magnitude. But if it's a multiplicative error, as the level increases, you get bigger like errors. But it is a bit difficult really to distinguish that from an additive and multiplicative seasonality where you have both of them there. So that's why we didn't talk about it much there. Okay, so now we can, of course, use exponential smoothing with multiplicative seasonality to handle this. So, and we can also stabilize that multiplicative seasonality that we see here, because the variance actually changes from here to there. We can use the transformation, and this is something I want to talk about first. So how to forecast with transformations. So, and sometimes this is helpful. I think I mentioned it yesterday. If you are interested in getting strictly positive or non-negative forecasts, the point forecasts that are strictly positive or non-negative, I would say, because sometimes it may happen. So sometimes when you apply a model, the sort of models we covered here, you'll see, oh, maybe the point forecast is negative. If that's the case, then you can do transformation. There are other ways to fix this issue, but one way that might be effective is to use a transformation like Box-Cox or log transformation. So here we can use a Box-Cox transformation if you like. So the variable that we have is turnover, and then this has different parameters for lambda. So depending on the value, sometimes actually this corresponds, the value that you put here could correspond also to the lag value. To the value of the lambda, if it's 0.5, could be similar to the log transformation as well. Okay, so if I do that transformation and I run, now you see that I actually, by that transformation, I could stabilize, that variance that we see here. And this is also common. This transformation could be used to stabilize variance there. So now you still haven't done, of course, the modeling. So how do we do the modeling? Well, I take my data, I pass it to the model function, I call it ETS if you like, but again, this is the name you provide. And then I type ETS. Now, if you want to use a transformation here, well, let's put this. So if I want to forecast turnover as it is, this is what I see. If I want to include a transformation, for instance, a lag transformation, this is what I need to do. Okay, I just put the transformation function before the measurement. If I want to use exactly what I had here, so I can just copy basically this and put it here. So this is what happens. So you just put the function before the variable that you want to forecast. All right, so if I do that and put it inside a new name called fit, if I check, now I have actually a fitted model, and then it tells me it's AAA. So it has an additive trend and additive seasonality. So if I do this without that transformation, Now this time it goes for multiplicative one. But the transformation that I applied, it made it simpler. So instead of having a multiplicative seasonality and error, it turns it to be additive error and additive seasonality. So that's how that transformation affects it. I just put it as a comment here. So just for your information. Now, when it comes to forecast, as I said, it is really easy. I pass my model table to the forecast function, right? So always similar. And I provide the numbers that I want here, either as a plain English, 3 years. And remember, when I said years, because I have a monthly time granularity, so this horizon means 3 times 12. So this would be the same as this. Sorry, it's 36. All right. So you need to remember that. I always try actually to use this because I know that I provide that number and I know the granularity, it is crystal clear to me. So that will avoid confusion. So I forecast for, well, let's say for 12 periods ahead. And then I can put it inside FCT as well. So this will be my forecast. I can also go and plot it, auto plot. And then if you want to include the actual, you can do it as well. As you can see, because I have lots of history, maybe it is not very clear. You can do now different things here. One thing that I tend to use, and I like it, is filter index. So I say filter index this data. Here I need to say, for instance, from 2018 January until the end. If I do that, so I'll see just a part of my historical data and I see better the forecast. You can change this if you like to 16. You'll get more information and see how this captures actually that information. All right. Now let's use the generate function. Produce forecast using bootstrapping. Okay. So I use the same fit that I created before for the time series. So I type fit and then, oops, generate H is 12. Now, I need more arguments actually here. The first thing I need to provide is how many I want to produce. As I said, you can go to any number, but remember, when you have 1,000 possible futures, it takes time to run. Okay. And again, it depends on how many time series. If it's just one time series, it might be okay. If it is many, then you need to be careful. If the time is a concern. And then another argument that you need to provide here, you need to say, I'm using bootstrapping. Actually here, because I have only one model and it is monthly, it was pretty quick. So I can have now those 1,000 possible futures. Let's say, call it a simulation, because we simulate different possible futures. And if you want, I can also go and plot them. Okay, so I take my data here. And then I go and say, ggplot. I want an aesthetic, my X to be months. Basically, there's months here. All right. And then I will add a geom line to this. And then the aesthetic that I use here is turnover. Basically, it is what I have here, right? I need this turnover here. So if I just do that, well, actually, nothing happens. ggplot, extend, months. Okay. Okay, and then zoom line Y. Okay, so that's the time series. And then I want to add now another geom line. And this time I say that I want my Y to be .sim. Sorry, that not, I call it simulation. All right, so I want, is it, what is the name inside this? Is .sim actually, simulation. So I want to use .sim, right? From this simulation. This is what I created here. And these are all possible futures that I have. All right. And then I want also to give different colors. And then here you see many, many different colors to different replications. So this .rep, it's related to times. How many times? And I want this to be a factor. Just a data type in R. So another thing that I want to highlight here is I have to say what is the data that I use to create this geom line here. I'm not using the Cafe Vic because it doesn't have that data. It doesn't have the simulation, right? So I need to say this is actually the data that I want to use, the simulation, because it has this information that I need, .sim, which is this column, and then .rep, which is this column. Okay. So if I run this, let's see what happens. I think I may need actually to make this color false. Otherwise, I think I see lots of colors there. I think hopefully this would work better maybe. Yeah, I made a mistake to show the legends because you have many colors, 1,000 colors, it will show them, and that's what it wouldn't run, but let's see if it would. Okay, let's see if there is a question here. When modeling, is it advisable to use all the time series at the beginning or filter first? Well, this depends on what you want to do. It depends on the question you want to answer. If you have, if you work in a pharmaceutical supply chain and you have, I don't know, 50 time series that you want to forecast, well, you have 50 time series. So you don't filter, you just forecast all of them. So it depends on the question that you are answering. If you care, for instance, here, if I care about there is some errors here. So if I, in this case that I'm showing you, if I just from this data set of Australian retail, if the one I manage, I care about, I have to use this forecast to do something with, is about Victoria, and then about cafe, restaurants, and catering services, then I just go and focus on that because I don't care about the rest of this, right? That's why I go and filter, and then I do my analysis and forecasting. But if you care about everything, well, you forecast for everything. But then visualizing, for instance, that would be a bit difficult. I think another thing that, so I can do maybe this filter index here, just to show you that as well. Okay, so if I run it, now you see that all possible futures. So I generated 1,000 possible futures there. Right, so you could do the same thing with the forecast. So if I pass the fit to forecast, so I do the same thing here, basically, but I replace generate with forecast, and then I don't need to provide the informations that I have about times, because by default it does that. And then let's say FCT bootstrap. Okay, if you run that, this is now what you see. So if you don't provide anything here, by default it goes and generates 5,000 samples. So if you remember when we generated that, I said 1,000. So it goes and puts it inside simulation. So in this data rep, I have from 1 to 1,000 different samples. But the forecast by default, it uses 5,000 samples. And it put them all together instead of showing them as .sim, right? So in .sim, for each point, it gives you what is that possible future. But if you use the forecast function, it grouped them together and represented them as a sample of the number of times that you produce the forecast. So I think we can also do the sort of thing we did before with this. I mean, you can extract, so if I take the simulation one, because this is what I have, right? So if you want to get prediction intervals, so you cannot get prediction intervals, for instance, from this. Let's say if I put level 90, it gives you an error. It doesn't work with the simulation. So there was a question before about when I use forecast, when I use simulation. That's another thing. But you can do a lot of other things with simulation as well. You can get this .sim and create distributions for each month, create histograms, for instance. But you cannot extract prediction interval from it. For that, you have to use forecast. So that's how I create prediction intervals. And if you want also to create a distribution in a visualization form using forecast, it is a slightly easier because we have already functions for that. So we have done it, and I do it again. So I take basically what I have here, right? And then I put here X in the months, and then I put Y dist in turnover in Y dist. Okay, this is what I have here. And then I add what I want to show, stat, not a state, stat of I. And so let's see what happens. Okay, didn't, oh, okay, sorry. I need to take my fable first and pass it to ggplot. Okay, so this is what I get. So what if I add the auto layer to this as well, or I could add the geom, for instance, aus Café Vic. Okay, so we can get that, but again, this is something we cannot see clearly. So I would go and copy basically this and paste it here, and that should be better. Maybe I will make it 2017 or even 2018. Okay, so now we have the point, I mean the reality, what we observed actually, and then the distribution as well. And then this now gives us how for the next 12 months, how distribution changes. These are the point forecasts, so the middle of the distribution. But as you can see, there is a bit of uncertainty. And as we go from 1 month ahead to 12 months ahead, you see that uncertainty increases there as well. Okay. I think that was probably what I wanted to talk about for the exponential smoothing. And then now we can go and talk about ARIMA. Is there any question? Anyone before we move on? Okay, if there is no question, let me just open my slides. Okay. Okay, should be able to see my slides, right?
Yes, it's visible.
Yes.
Thank you. So in this session, I'm going to introduce a new family of models that we haven't used before called ARIMA. So I talk about what ARIMA models are, which sort of systematic information they capture or they take into account, and maybe how they are different from others. And then we talk about seasonal ARIMA models, because we can have an ARIMA that has only non-seasonal components, but we can also have ARIMA models with seasonal components. And then actually at the end of this, I introduce another topic called forecasting ensembles. This technique combines forecasting from multiple methods. And here we look at how we combine exponential smoothing ARIMA and seasonal naive, for instance, together. Instead of using them separately, why not to combine them? And this is a research area called forecast combination or ensembling. Okay, so what ARIMA stands for? Autoregressive, integrated, moving average. One thing that I want to emphasize right from the beginning is you shouldn't confuse moving average component here with a smoothing method that is called moving average. So there is a method similar to simple exponential smoothing called moving average, and where you can take certain number of observations and then take an average and move forward, and by doing this you get a smooth version of your time series. This is completely different from the moving average here. Okay, so the AR component is related to the previous observations. The integrated part is about a concept called stationary, and we'll talk about this in a minute. So if you have a time series that is non-stationary, ARIMA needs to actually make them stationary and then can work with the time series. If it is non-stationary, you cannot. That's the assumption that comes with ARIMA. ARIMA works with stationary time series. So if you have a non-stationary time series, the function we use automatically makes it stationary and then do the rest. And moving average is about the relationship with the previous errors or the residuals that we have. So ARIMA can get or take into account the previous observation or lagged observation. It can take into account also the previous error terms or lagged error terms as input. So in exponential smoothing, you know, we had level, trend, and seasonality. And actually, it is quite easy to understand these systematic patterns because we have observed them and we visualize them, and then we know how exponential smoothing take them into account to create the forecast. ARIMA models are not as interpretable as exponential smoothing models, but they are amazing because they can capture so many different time series sort of behaviors by the combination of these components, but also the parameters of these components. They can represent many different time series. So the first thing we need to understand is this concept of the stationary. Well, we say if we have a YT, which is our observation, we say that YT is a stationary time series. So again, T changes from 1 to 2 to 3 to T, which is the last observation. If this is our time series and it is a stationary, then for all S, the distribution that we look at for that range of S doesn't depend on T. So this is something like if I draw, for instance, a time series, something like this. So basically what this says is, if I take a window of, maybe I use a different color for this. If I take a window of same size called S here and S here, and remember this is the time series, right? So here I have my observation, and then here I have my time. So basically what stationary says is, if you look at this window of S in this time series and go and create, for all these observations that you have here, create a distribution using, for instance, a histogram, the distribution of this part and this part should be similar. That's the concept of a stationary time series. Now, a time series that is stationary is roughly horizontal. So it's something like that. So you can see it, something similar to basically the level, but of course with the randomness around it. It has a constant variance. So it means it is not something like, if I give you an example of this, for instance, if you have observations where the variance changes over time, so it means here you have something small and then suddenly something, something bigger, for instance, happened that shows the variance that changes. Or in the seasonalities, if you remember, if we have multiplicative seasonality with the trend that we have, something like that. So again, this is something, it means the variance is not constant. So if you deal with something like that, it means your time series are not stationary. Okay, so the stationary series is roughly horizontal with constant variance, and actually there is no long-term predictable pattern, because remember, if you have seasonality, they are predictable, because we know that if future and past they are similar, you will observe those consistent pattern in the future as well. So they are, in long term, they are predictable. But if we have a stationary time series, it means we have no predictable pattern in long term. And actually, this kind of idea could be useful for cycles, because cycles, they are not really predictable like seasonals. So if you have this sort of information like seasonality and trends, it means you are not dealing with a stationary time series, but non-stationary time series. I think it would be helpful actually if I just show you one example that I have in my book. Yeah, so if I share my screen again, should be able to see it, right? So this is an example of a stationary time series. As I said, is roughly horizontal with, of course, variations around this. The others that you can see are example of a non-stationary time series. So here you can see clearly that, there is a increasing trend. So if I look at this window here and here, the distribution would be different. Again, here I have a change of level. So if I look at the distribution here and there would be different. Here is very different from here. Here is very different from here. This is an example of not having a constant variance. And then here again is very different from the others. So these are some examples of a non-stationary time series. Okay, let me actually ask you then one question. I will share this in the chat. So if you don't mind, please click on the chat, look at the chat and click on this link. And then if you click, you should see this plot, or you can look at the screen actually if you want and take some notes and then go and vote, right? So we have A, B, C, D, E, F, G, H, I. Can you tell me which of these series are stationary? How it works, but you can vote. You can select multiple options. Okay, I show you plots again. So if you look at the time plot of this, which one you think is stationary? And of course, the rest would be non-stationary. So one way to understand whether a time series is stationary or not is actually to simply plot it. And then there are other ways that you can do. You can even do a statistical test. Let me see how you do. So we have B and G. It seems like B and G are very popular. Okay, because you could vote multiple times. I think I can see 30 people voted. If you want, you can, maybe I'll give you one more minute. If the rest you want to vote, then we can have a quick discussion around this. Okay, so I have 30 votes. So yeah, most of you think B and G. Actually, you're right, because if you look at the rest of them, you can see that the sort of discussion that we had around looking at the window and having the same sort of distribution is not valid. And so here you have the sort of change in the level, but also trend. You have trend and seasonality. Here you have seasonality. You have trend. You have seasonality. So B and G are two options where here I have a sort of stationary time series, so which is change in Google price. Actually, the one before is the Google price, Google closing price. But here I calculated difference between adjacent days. So YT minus 1 gives me that, and that makes that to be stationary. Here, actually, this is a cyclic. There is a cycle here. And I mentioned in the previous slide, if you are dealing with a time series with cycles, so you could use ARIMA. There are certain conditions, but because they are not predictable in long term, so you can use that. Okay, so that's great. So it means you have a good understanding of stationary and non-stationary time series based on time plots. So, well, this is, I think, the example. Now, the thing is, what if you have a time series that is not stationary? Well, what we can do is you remember we previously did transformation. Transformation is one way to stabilize variance. But in the sort of examples we have seen, you may need to stabilize the mean, and differencing helps to do it. So the difference series is the change between observations in the original time series that you have. So when you calculate one difference, you calculate the difference between each observation comparing to the previous one. So how many differencing do we need? Well, it depends. Most of the time, one differencing would be enough. Sometimes you may do two differencing, but I don't think you need more than two order differencing to make your time series stationary. Okay, now let's look at some models separately, because we talk about ARIMA. So they have different components, AR and MA. And actually, if we take out I, it means we have ARMA. So it means we are dealing with a stationary time series. So this is the equation for the autoregressive or AR model. So as you can see, we can separate just AR and use it as a model, right? Not having everything together. And this actually looks familiar, isn't it? It's kind of similar to the multiple regression model we saw yesterday. So the observation impurity equals a constant plus a linear combination of previous observations until observation YT minus P. So it means I need to include P, previous observation, in this model. So the question is, what would be that P? This is something we call it an order. So we have to determine the order of P. It means how many previous observations we could include in the model. It could be 0, it could be 1, it could be 2, it could be any number that we can test there. So that's one thing that we need to determine. So in addition to that, we need also to estimate these parameters. We call these parameters phi. So phi are related to the autoregressive part. Of course, we have the epsilon part, which is again a normal distribution. We have to also estimate the standard deviation of epsilon t as well. There is a part here called C, constant. So we may include the constant or not in the model as well. That this is actually related to the mean of the data as well. So there is a relationship between this constant and the expected value. If you want, you can calculate that as well. There are actually some functions that you can use in R to simulate ARIMA models in general. So you can simulate an AR1. It means I have only this part, of course, plus epsilon. AR2, it means I have this plus epsilon. So, and depending on the value that you provide in this value, again, they have certain conditions. If you have only AR1, so this phi can change between -1 and +1. So, and remember, depending on the value that phi takes, the shape of this time series is very different. And that's what I mentioned at the beginning. ARIMA models, they handle this quite well. And then we could have a moving average model. I don't know how, I mean, realistically, how these models are useful in practice, but at least I haven't seen anything myself with the MA1 separately, but AR1s, of course, they are very helpful because remember, they try to explain the association between what we want to forecast and then the previous observation, which is, you know, something that makes sense to us. But this model MA, they are trying to link the observation to the error terms in the past. And then here we have also an order called Q. So we have to decide how many of those orders we need to include. And following that, we have to estimate the parameters as well. So if we say we just add one error from the past, so E epsilon t minus 1, it means Q is 1. We need also to estimate the parameter of the theta. We need also to decide whether we include C or not, and then also estimate the variance of that error. And again, you can simulate this, and depending on how many Q we have and the values of the parameters, you can simulate many different shapes of the time series with MA1. So you can have a combination where you have both the AR part and then MA part, and of course the epsilon and C as well. So, but the idea is similar. I have to make a decision how many P, how many Q, and then estimate the parameters as well. Okay, so now if we have a stationary time series, this is the equation that I get for it. If my time series is not stationary, so I have to calculate a different thing and then go and choose PDQ and decide whether to include C or not. So this is something that we need to be aware of, and that's actually make it an ARIMA model. So when you say ARIMA, we have PDQ. So we say, what is the value of D? So D could be 0. It means no different thing. It means the time series is stationary already. If we need different things, so we provide that. And then we need also to determine the orders. Now, depending on which value this PDQ take, we get some models, they look familiar. We have seen them before. So if we have a PDQ equal to 0, we get an ARIMA 0, 0, 0. Basically, this corresponds to a white noise model that we saw in day 2. If you have an ARIMA model where you have only different thing, and then P0Q0, this corresponds to a model called random walk. This is actually the model behind naive method. And then if we have ARIMA 0, 0, 0, 1, 0, but this time including the C constant, we have random walk with drift. Again, this is what we have seen. This is the model behind the method that we have seen here. And remember here we have the model because we have the epsilon. We can have also ARP, so it means we don't have D and Q, or MAQ, it means we don't have AR and I here. So we can use them separately if you like as well. So I can go maybe and show you one example in R. And then we'll come back to discuss about some other important aspect of the modeling, including how ARIMA works in general. Okay. Okay, so let's put ARIMA here, ARIMA here. So I'm going to use one of the examples that maybe I used before. So I can do this one. So I just copy what I have here. So in global economy, I filter country. I could actually do something else, like there is another column here called code. So this code, I say this time, well, let's take, you can look at different countries, but I could look at Egypt, for instance. So I can filter that, and this is what I would see. So the name is quite long there. That's why using the code is better in this case. Okay, so if I want to, well, you can go and visualize this if you like. Let me do that before modeling it. So auto plot. And this is automatically takes GDP, but we could, for instance, go and take export. So if I don't provide anything, it will go and take the first measurement that you have in your data. So it took GDP by default, but I want to visualize export. So I have to specify what I want. And then I get something like that for the export. Okay, so the next thing that I need to do, maybe I can just separate them to be able to use them. I say Egypt economy. And then I put something like this, so to visualize it. And then I can now go back and use this. Okay, so to model it, I pass my data to model function. I give a name. And then the function that we use for ARIMA models is called ARIMA in capital letters. Again, this is a new function. You need to remember that. So what is the variable I want to forecast? Well, it is exports. And then I call this a fit. Save it in fit. And I can go and look at the fit. What happened? Is it? Okay. Model ARIMA and okay, it's fine. Export ARIMA. Okay, I can look at the fit, and then I have one model. So, and then one time series, you can look at the report. So what it tells me here, it returned the model called ARIMA 201. So it didn't use any different thing. It has two AR components, and it has one MA component. And then, of course, the constant as well. So if you want, you can actually write down this equation. So if I write it, it would be something like this. I don't know whether you can see it here. But then we have that YT equal 2.56 plus, now I have two of this component, so I have 1.67 for YT minus 1. plus, okay, so that would be minus, actually, minus 0.8 yt minus 2, because is AR2, and then minus 0.68 epsilon t minus 1, because it's MA1, right? So that's how we do it. So this corresponds to that. This corresponds to that first equation there. This corresponds to that equation here. And then here we have the MA1. So you can go back always to from the model here to the equation. And you can also here get an idea of the variance of the error term as well, the epsilon. So this number here, this sigma square estimated, corresponds to that value in epsilon as well. Okay. So let me just get rid of this first. So what is next? Well, next you can just go and take the fit, pass it to forecast, and then put a H there. You can forecast for 5 years or 10 years or any number of years you want. So you get your distribution, the point forecast. If you want, you can visualize and do anything that you like, and we have done it before, I'm sure. As you practice more, then now you know how to visualize the forecast, even with the distribution, which is actually something quite new to all of us. All right. So let me go back to my slides. So when you apply the model function automatically, and I will tell you in a minute how that model exactly works, but the function is ARIMA in capital letters, as you see. And then when you apply that, it goes and look at the possible values of PD and Q and returns one, and we see that one when you use the report function with the Mabel with the fit. It tells us which model has been returned, and it tells us also the estimated values of the parameters of that model. Okay, so now there are some aspects of ARIMA that we may need to understand better. So one important thing is this: the value of P and Q that we determine has an impact on short-term forecasting. But for the long-term forecasting is actually the C and the D, they affect that, right? So if you have C equals 0 and D equals 0, the long-term forecast will go to 0 eventually. So you will have maybe something that changes in short term, but in long term that will go to 0. Now, if you have a C 0 and D is equal to 1, the long-term forecast will go to a constant value that is not a 0, because we have a differencing. If you have more than one differencing, then the long-term forecast will follow a straight line. Now, if you have a constant value that is not 0, but there is no differencing, then the long-term forecast will go to the mean of the data, average of your data. If you have one differencing, then it will follow a straight line. And if you have two differencing, then it will follow a quadratic trend like that. But this is something maybe we don't recommend really. So it is important to just get an idea of how this will affect the long-term forecast. So P and Q take care of more shorter-term forecast, and C and D are related to more longer-term. And of course, the variance of the forecast, it will be affected also by D, if you have the higher value of the differencing, the prediction intervals become wider, and then for D equals 0, the standard deviation of a long-term forecast will go to the standard deviation of the historical data. Well, this is something we could do. Now, the most important part of this is how ARIMA works, because we are using this function to provide us with the best ARIMA model. So what we mean by best, we will see in a minute. And then it returns the P, D, Q for us, and also the estimated parameters. So how that algorithm works. Well, this is discussed in a paper by Heidemann and Kandakar in 2008. And this is the main step of the algorithm discussed in this paper. The first step is to select the number of differences we need, which means the D part. And this happens with a KPSS test. So KPSS basically tells you whether the time series is stationary or not. Or it can also tell you how many differencing you need. If you remember when we discuss about features, we use a function called feature where we can extract a lot of features of time series. Actually, one of them is related to KPSS, and we can extract this feature, and I can show you how to do it as well if you want. So that's the first step. The second step is we select the value of P and Q and whether to include C or not. How? By minimizing the information criteria that we have discussed before. And then we do a sort of a stepwise search. We go through a model space and look at the different possibilities based on that search stepwise algorithm. And this is the information criteria for the ARIMA. But again, what is important is information criteria. What is important to understand is every information criteria we have shown you for regression, for ETS, and then for ARIMA, they have two parts. This part is about the likelihood, the logarithmic of likelihood, which is about the fitting. How good is the fit? How close the fitted line is to the actual observations. And this part is a penalty given to the number of parameters. And as you can see, now we have now P and Q. We have also K. And K, if you have the constant, is 1. If there is no constant, is 0. So this is the AICC that is used in the ARIMA model that is returned as an output. So one important thing is you need to be careful actually with information criteria because if you have different differencing, you cannot use information criteria because then that likelihood has been calculated based on different data. And this is why you cannot use information criteria to compare between different family of models as well. You cannot compare AICC of exponential smoothing with ARIMA because they have used different data to calculate the likelihood. So again, this is something important to remember. You can use it within the families, they're using the same data. Okay, so the first step is this. We determine the D, and then we start with these models. So an ARIMA 2D2, ARIMA 0D0, ARIMA 1D0, ARIMA 0D1. And then, as I said, we determine DB4. And then from these 4 models, we select the one with the smallest AICC. And then we consider variations of the best model we selected from here by changing P and Q. So +1, -1, and in different directions. And then also including or excluding C. And when we do these changes, again, we look at the AICC, and then we see which one has the lowest AICC. And that be the current model as a base to go and search for other possibilities. And we repeat actually this until we find the lowest AICC. It is easier actually to show it like this in this diagram to see how the search works. This is something we call it a model space. It's a different possible combination of P and Q. So P changes from 0 to 6 actually, which is not visible here. And then Q also from 0 to 6. Well, of course, it could be even higher than this if you like, but maybe it doesn't make sense for many examples. So the first step is we had those 4 options. We go and see which one is the lowest AICC. Assuming this was the lowest AICC, this then becomes our current model. Now, what happens after that? We have to go and look at the neighborhoods of this model. So we go now and check, then P becomes 1, Q becomes 1, P becomes 1, Q becomes 2, P becomes 1, Q becomes 3. So we go and check all the neighborhoods of the best model. And one of these would have a lowest AICC. This would be, for instance, this one. Then this becomes our current model. From here, we go and check the neighborhoods. But remember, I don't go and check this. Why? Because I have already checked them. So the neighborhood then becomes only this green spaces. So I go now and check all of them. And now this becomes the lowest. And I keep actually doing it until where I find out this one from the search that I did here has the lowest AICC, and stop there. And as you can see, from the entire model space, we just check the one, you know, with the step 1 with orange, blue, green, and this colors, right? So we didn't check really all the possibilities. But this is how the algorithm checks. It is possible that one of these would be slightly better than the search that we have done. But remember, sometimes suboptimality is not a big deal. Sometimes it's better to be suboptimal, but you save a lot of time rather than trying to be optimal, but with marginal improvement. Okay, so we could have also a seasonal ARIMA. This is exactly like what we discussed for non-seasonal ARIMA with PDQ. We could have a capital P, D, and Q, and then here M determines how many seasons actually we have. Okay, M is 12 for monthly, M is 4 for quarterly, etc. But here we have also a differencing called seasonal differencing. So this differencing is not seasonal, this differencing is seasonal. So if you have a seasonal differencing, it means, because the differencing here, it means you calculate the difference between adjacent observations. This month minus the months before minus the months before, and so on. But if you have a seasonal differencing, you calculate the difference between seasons. So January 2023 minus January 2022. January 22 minus January 21, and so on. That's what this actually means. And then these two components are, so the way we combine them is we multiply these two components together. So I will look at this example from the pharmaceutical sales. And then I will talk about the ensemble as well in the R session. So the ensemble one basically is quite straightforward because we have a model, and then we train the model and the data. But then if it is one model, it's fine. If it is more than one model, we have a chance to use a forecast that is produced by a combination of these models rather than using them separately. And this is what we call ensemble forecast or forecast combination. And it is extremely easy to do it with Fable. It is not always easy, I would say, with maybe some other packages, but extremely easy with Fable. So if you want ensemble forecast or forecast combination, you just take the name of the models that you have inside the model. Of course, this needs to be inside a mutate. It means we want to create a new model called mixed combination, whatever name. So we add these models together, ETS plus ARIMA plus S-naive, and divided by 3, it means we take a simple average of them. So this will not only calculate the point forecast, but also will take care of the distributional forecast, prediction interval, and anything else there. Let me see if we have questions, and I can go to the R just to show you this a little bit. And so there are 2 questions. The auto ARIMA that you mentioned there is from another package called forecast package. Here we are using Fable is the new ecosystem for doing tidy time series forecasting. So basically, Professor Heinemann, who is behind this with Mitch and others, he created the forecast package previously. I think it is still functional. You can still use it. So auto ARIMA is from, if you mean that, I'm not sure whether actually we're talking about the same thing, but because that function is, that name is a function in a package called forecast. So that auto ARIMA and ARIMA function that we use here, they are doing the same job.
Hi, Bahman. I've shared a question that was sent to me directly.
Okay, my concern is about the significant gap between the actual and forecast plus while we have a time series. What if a join together to see a continuous curve? What if are joined together to see a continuous curve? I'm not sure if I understand that part. But when you say the difference, the gap between actual and forecast, we haven't covered that at all. This is the topic of tomorrow. So tomorrow we talk about how we evaluate the performance of models, including looking at the residuals and looking at the forecast accuracy evaluation. So again, if you talk about, I'm not sure what you mean by compare, but if you mean how accurate they are, we haven't talked about that. It is the topic of tomorrow. We will cover tomorrow how to evaluate the accuracy of the models, what is the difference between residuals, the forecast error, how we evaluate the point forecast, the prediction interval, and the entire forecast accuracy. This is something we cover tomorrow. Okay, so let me briefly then go through one more example. So this example is about pharmaceutical products, right? So this is the PBS data set. It's a monthly data set. And I'm going to focus on one item. So we have used A10, for instance, before, if you remember. So this is something similar to what we do now. So I'm going to focus on one that is this one, which is H02. Let me see. Yeah, so it is H02 from PBS, which is corticosteroid drug sales. Okay. Okay, so let's see. So this is H02. So if I filter that, this is what I would get. I want to focus on the column cost. Look at the cost of this item. So, let me see. Yeah, so it is H02 from PBS, which is corticosteroid drug sales. Okay. I want to focus on the column cost. Look at the cost of this item. So, 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 look at I will need to summarize. Okay, and then cost equal sum, not in capital letter, of cost. And I want to actually show this in million as well at the same time. So this will give me the total cost for this pharmaceutical product. This is the sales of this pharmaceutical product. And then let's call this H02. Of course, you can auto plot this to get the plot. So what do we see here? So we see that there is a seasonality. So we see that consistent pattern. There is also increasing trend, but it seems like the seasonality here differs from there. So as the level of trend increases, the seasonality length or magnitude increases as well. So I can go and do a transformation just to stabilize that. So I can do log transformation, for instance. Actually, that should be like that is better, and then that shouldn't be like that. So I will do that. And then here, what I want is cost. Okay, so here, if I do that, it will work because I have only one column, but that's exactly what we see here. And then stabilize the variance. Let's change a little bit. It becomes more and less similar. So the lengths here and there, now they are similar. Okay, do I need to do differencing to make it stationary? Well, there is a seasonality. So I need actually to do the differencing. So if you want to calculate the differencing, there is a function called the difference that can do that. Remember, this is a monthly time series. If I want to do seasonal differencing, then I need to do something like that. I think I need to do a mutate, not something like that. Let me just have a quick look. Okay, so it is plotting it, but let me check. It should be that one, isn't it? So we can calculate the differencing and then plot it. Well, you may say that there is still actually some sort of patterns there that I can see. For instance, something like that. So here as well. So that means you may also need to make another differencing. And that differencing this time is to stabilize the mean. So I can do also one differencing here. And this time I just copy this and then paste it just here. Okay. So now when you have this sort of like two type of differencing, one for seasonality, one for to stabilize variance and stabilize mean, or to remove the seasonality and then make it stationary, it is recommended to first do the seasonal differencing and then the other differencing. Okay. Now the thing is, of course, you can do it for yourself, and there are, the methods called Box-Jenkins methods in a Riemann model, where you go and look at the ACF and PACF. So PACF is partial autocorrelation, and this helps you to determine the order of P and Q. And as I said, you can do a test to determine whether there is a time series stationary or not. But ARIMA is doing that actually for you, right? But I will probably show you also that test called KPSS and how it works. So you can, for instance, take this H02 and then say feature. This is similar to what we have done before, right? We use features function. And then I have cost as the variable that I want to go and test. So whether for this time series, so there is a stationary time series or not. So the name is called unit root KPSS. This is actually what we need to do. And if I do that, it tells me the p-value that is calculated is 0.01. And this is based on a null hypothesis. So that the time series is stationary. So because it is smaller than 0.05, I reject that, and it means the time series is non-stationary. So you can also use this test if you like. Something similar to this that you could use is unit root KPSS, but this time you can use NDIFs, for instance. So NDIFs also tells you how many differencing that you need. There is another one for seasonal differencing. So basically it tells you you need one seasonal differencing and one differencing to make your time series stationary. So you can do this, this kind of thing as well if you like. If you want to calculate the ACF, and then plot it, so you know that to calculate ACF, we first use ACF and then autoplot. And this will give you the ACF or kilogram plot. And then if you want to calculate the PACF, you simply add a P there. So now what is PACF? So you remember in ACF, we look at different legs. So we calculate the correlation between different legs. So we have leg 1, it means we look at the association between adjacent periods. Leg 2, 2 periods apart. Leg 3, the correlation between 3 periods apart, right? But remember, if you look at the correlation between period 1 and period 3, well, you also look at the relationship between period 1 and period 2 and period 2 and period 3. Okay, so there is this relationship between them as well. If you want just to look at the direct relationship between period T and period T minus 3, not taking into account the relationship between them because it will affect that relationship, this is the idea of partial autocorrelation. So actually the ACF and PACF could be used to choose P and Q. And then the idea is go and actually pick, for instance, in the PACF, pick the latest significant leg, which is 13 here. And that would be probably an AR 13. You can start with that and look at the other possibilities using the search, for instance. But I don't really recommend to look at the ACF and PACF to pick the P and Q. I don't think there is much value in adding it like that. But you can look at it for yourself to understand basically how ARIMA works in general. This is a methodology called Box-Jenkins. So if you read time series analysis books, it is likely that you come across this. And this is how they select that. Looking at the ACF and PACF, they can choose the order of P and Q. And for different AR1, MA1, AR2, MA2, the behavior of ACF and PACF follows a sort of a pattern. So that helps you to determine P and Q. So for instance, just to give you an idea, for AR1, so for AR1, if you have ACF and PACF, so for AR1, you have an ACF that decays like that. And then you have a PACF with a huge lag here, and the rest very small. So if you deal with a time series that can be modeled with an AR1, so to pick that P value or P order, that is 1, if you observe an ACF like that and a PACF like that, that recommends you that is the good P to go for. Okay, so ACF and PACF, they would be helpful for that. Let me go back to my just R code to see where we actually left it. So yeah, this is the idea, was just to start looking at the different things, see if it is not a stationary. So we need to make 2 different things to make it a stationary. And if you want, you can also look at ACF and the PACF, but also the KPSS test to see whether this is a stationary or not stationary. So the final thing that I want to do is just to go and do the modeling, right? So I take basically my data, which is H02, and then I go and model. I just call it an edema, and then edema. I can actually use the transformation to stabilize that multiplicative behavior at the beginning. And then I can use now the variable that I want. And then I can pass this to the forecast function. And I can provide an H that I want. Let's say 3 years. And that gives you the forecast. If I want to maybe separate the fit from the forecast and then look at the fit as well, you can also look at the fit. So if you look at this, actually what it returns is, it returns that seasonal edema, because you can see that 12 there. And so P2, D1, Q0, and again, the capital D1, because we have one different thing in both seasonal and non-seasonal side. And then it picks also one Q here as well. So when it comes to the seasonality part, it is quite similar to the way we build the model is seasonal to, I mean, the concept of it is similar to the non-seasonal part. So these are also the coefficients of the equation, and then the variance of the sigma, which is about the error term. In the exercise, I think I can provide you some additional code where you can simulate different edema processes and see actually how they behave. Okay, so I think we are 5 minutes beyond the schedule. Just let me see if there is anything here. Okay. Okay, I think let me just show you how we do the ensemble as well in 5 minutes, and then we can end it. Sorry for that 10 minutes. So if I want to do the ensemble, and this is I think a good thing to have in your toolbox as well, instead of using one simple set of separate models, why not having a combination? And sometimes it could be helpful. There is a good research actually behind this. And people show that the combination can improve forecast accuracy. So let's say I use the data for the tourism that we have. And so it's tourism. So this is the data set. I can use all the data, but I could also maybe filter and just use few of them, or maybe I could go and focus on what we had done before, and one, for instance, purpose of travel, if you like. Or what if I just go and say index by quarter, and then summarize. So in that case, trips would be sum of trips. So if you do that, basically here we have the total tourism for the entire country. Okay, so instead of looking at now many time series, I'm just interested in the tourism in Australia, in the total country. So that's why I will have one time series only, just quarterly. So the index and the measurement. Okay, so what happens then? I take my testable, I pass it to model, and then inside this, I want to create different, let's say I will start with seasonal naive. So I have a seasonal naive, and then this is what I want to forecast. Then I will use an ETS as well. And then I would use an ARIMA as well. Okay. So if I run this, I have here, sometimes I think, okay, so it's, sorry, I just misspelled this. You need to remember that, okay? So this is a function name for ARIMA or for any other forecasting model in Fable. They need to be in capital letters. And you may choose a different name to avoid confusion actually between this name and that name. So I can, I think, quickly do that. So let me remove those names. Why those names could be interesting. So do you see when I had that names, they become the column names. If I don't have any name there, this is what I see. So that becomes the name of the column, which is different from what we had here. You can actually compare them now. When I have names, when I don't have names. So I recommend to always have names. I keep them like that. So we take the testable, we pass it to a model, we put any number of models here we want, and then we pass this to mutate. And then I call this a combination. And I want to get a combination or ensemble of these three models that I have here. So I simply add the names together. All right. And then I put this inside the fit. So this will train these models and ensemble on the data. And then I pass the fit to a forecast. Let's say I forecast for 12 steps ahead. Okay, so you get basically the forecast for all these models. and then I will include the data there as well. So now you have basically an idea of the forecast using these different models. So seasonal life, I think, so it is here, but so there are 4 or 5 different colors, and there are also overlaps, so it is not very easy to see. But that's the idea, is to generate the forecast, the point forecast, prediction interval, and then the distribution as well. I just show you actually here, maybe you cannot see it, but I will show you. So if you look at here, you see that as well. Now I have seasonal naive, ETS, ARIMA, and then a combination. And then for the combination, I get the distribution and also the point forecast. All right, so not only I can use the benchmark, the exponential smoothing in ARIMA, but if I want, and regression, of course, I want also, I can, and I want to create the ensemble. And the ensemble is simply an average of them. I mean, there are different ways to create an ensemble. I think you can stick with the simple average of the models, and that should perform quite well. So do we have a constant in this case? I'm not sure what is the question about. Maybe it is about something that I answered previously, but if you can clarify. Yeah, you can add the regression model if you like, it's not a problem. So if, let's say, so regression, but again, which models you combine is also an important question. So TSLM, so you can do that. And then if you want to add regression to this, so then I will add them. And this time I have to divide by 4 because I have an ensemble of 4 models. Okay, but the code wouldn't change much, is very similar. This time, if I produce the forecast, now you see that I have the forecast for regression as well, which it doesn't actually do well here. Maybe I will go and add trend and then the season. Okay. So yeah, you can add any number of models for the ensemble, but in general, when you do ensembling, it is good if you add models. I mean, something like this example. So if you have a model, let's say they forecast like here, and another model they forecast like this. So I think you agree with me, and assuming that my actual is something here. So let's say, let me use different colors for this. So if this is the forecast from one model, this is the forecast from another model, and then your actual is something around here. So I think you agree with me. If we add these 2 models, this one and this one, the average of them would be closer to this line. Okay, so if you have something like those and you take the average, it becomes closer to actual. This is where ensembles would be really good. Okay, so after fitting the ARIMA and then forecasting, are there forecasting in the original scale? Yes, so everything is going to be in the original scale. So whenever you do transformation, everything is transferred back to the original scale to get the point forecast, prediction interval, and anything else. Okay, I think, do we have a constant in this case? I'm not sure what is the question exactly, sorry. But if you want to maybe clarify, I'm happy to maybe answer that as well. All right. think that's it for today, really. So we have covered basically all the models we wanted to cover for the training. So tomorrow, we are going to apply everything that we have learned, but our focus would be on the performance of these models, how we know these models capture the systematic information, and how we evaluate the forecast accuracy for point, prediction interval, and distribution. So this is something we discuss tomorrow. I think it is going to be exciting because this is one of the most important steps in the forecasting workflow. I think I'll stop the recording here.